Good day, I'm J Wildberger. Today we're going to be looking at the connection between certain types of polynumbers, algebraic expressions in the Boolean world, and Boolean functions, which sort of encode the effects of electronic circuits made out of gates. So here's the example that we were looking at last time. We were thinking about three inputs, A, B, and C, and here's a particular Boolean function in this situation. So the 8 possible inputs, values of A, B, and C, and the outputs 1, 0, 0, 1, 0, 0, 1, 0. And we saw that this thing could be expressed in the algebra of Boole by this particular, like a polynomial or polynumber, or in the Boolean algebra story with bars and circle sums in this fashion. And so I need to remind you that our convention is that the algebra of Boole is primary, so we're going to reserve the addition for the main operation in that context, which is specifically addition mod 2. Okay, that's what the plus sign means. And this circle plus sign is the inclusive OR. This is exclusive OR. This is the inclusive OR. Okay, so the third kind of ingredient here is an actual logic circuit that encodes the Boolean function. And we can create one like this more or less directly just by reading either one of these expressions and converting the operations here, either addition or multiplication, to the corresponding gates that represent them. So in the algebra of Boole situation, the plus sign is represented by an XOR, that's that gate there, and the multiplication is represented by an AND. So this whole thing here can be interpreted as follows. Here are inputs A, B, and C, and here's also an input of 1. So this is like a constant circuit that's just always on. So 1 plus A, that's the effect of taking the 1 plus A and feeding them through an XOR gate. So 1 plus A is coming out here. And B plus C, that's the result of this gate here. And so 1 plus A plus B plus C, the first 4 terms here, is the result of taking an XOR on them. AC, we root A down here and combine it with C. And there's an AND gate representing the product. And this product here, A, B, C, one way of expressing that is to take the output of the AC that we've had and make another AND with the B. So there's a B coming in there. So this AND here will result in A plus A, B, C. And then the effect is that we need to combine A and C with, there's AC coming out of there, with what we had before. So that XOR adds that to that. And then finally the ABC is added on to that to give us the output F. Okay, so we have here the Boolean function. There it is right there, it's F. It's one out of 256 different possible outputs that can be established with these 8 different inputs. It's a function from B2 cubed to B2. On the other hand, in the algebra of Boole, here's the Boole polynumber that encodes this. And here is a logic diagram that captures the situation. So these 3 kind of elements are the basic nodes of a situation that electrical engineers have to become familiar with. How to go from one of these nodes to the other 2. How to convert from this to a gate, or from this to an expression, or from an expression to a gate, or from the expression to a truth table, and so on. Now, usually in electrical engineering courses, this is all done in the context of Boolean algebra. And the algebra of Boole story that we're making primary is almost not mentioned, or only obliquely or indirectly. What we're doing is we're trying to position the algebra of Boole as being central. So we want to understand the connection between Boolean functions like this, Boole polynomials like this, or polynumbers like this, and various logic circuits that represent them. So at the end of today's video, we're going to have more experience in understanding what exactly the relationship is between the Boole polynumbers and the Boolean algebra. And we'll be able to then have a very algebraic way of telling whether two circuits are in fact equivalent. So let me give you a quick review of polynumbers. These are sort of data structure points of view towards polynomials. We are trying to finesse the difficulty in defining what a variable is. Okay. Usually we say a polynomial is, an expression in a variable x or in a variable z or something, and that's problematic because it's very tricky saying what exactly a variable is. So in the one-dimensional case, we have a situation sort of like this. A polynumber is a column of numbers. There's a polynumber p, there's a polynumber q, there's their sum, which is just component-wise, and the product is obtained the following. The top one is 1 times 2, the next one is 3 times 2 plus 1 times minus 1, the next one is 2 times 2 plus 3 times minus 1, and the next one is 0 times 2 plus 2 times minus 1 plus 3 times 0, and so on. Now, to introduce something that's a little bit like a variable expression for it, we introduce alpha to be this particular polynumber, 0, 1, in which case alpha squared is 0, 0, 1, and so on. And then we can write, say, p as 1 plus 3 alpha plus 2 alpha squared. So the alpha ends up playing the role of the x, usually. But now if we are asked what is alpha, we can say precisely what it is. It is this particular polynumber. So the role of a variable disappears completely. That's a very good thing. Okay, so here's the two-dimensional story. It's something similar. Now we have the possibility of having sort of two directions. So it's a two-dimensional array, 1, 2, minus 1, that's r, 3, minus 1, 0, 1, that's s. The sum is just component-wise, and the product is a little bit more complicated. And one way of understanding that is just to convert everything to sort of this kind of form. So if we introduce alpha as well as before, but now beta also, the polynumber 0, 1, that row 1, then alpha squared will be as before, but beta squared will be 0, 0, 1 in that direction. Combinations like alpha and beta are possible. That'll be the one down there. So then in terms of those things, so this thing here would be 1 plus 2 alpha minus beta. This would be 3 minus alpha plus beta squared. And then you can check that if you multiply these two polynomials in the usual way, just thinking of alpha and beta as variables, you're essentially getting this one here. It's just writing it down all the coefficients all at once. Okay, so that's the theory of bipolynumbers. Polynumbers here, just one variable, bipolynumbers with two variables. And we can carry on to higher dimensions also. So for example, if we go to dimension 3, polynumbers in, say, alpha, beta, and gamma correspond to three-dimensional arrays. And let me illustrate it through this example. So here's a polynumber in alpha, beta, and gamma. And the coefficients are certain numbers. And really the whole thing is dictated by those coefficients and their positions. And so we can put the positions on a three-dimensional sort of lattice. In this case, we just need a cube because the powers are not very big. So if here's the origin, and here's, say, the alpha direction and the beta direction and the gamma direction now, then this cube represents all those positions where the coefficients are either 0 or 1. And we see that the various values here can be represented by this assignment of numbers to the various positions. A 1 here, a minus 1 here, a 2 here, a 4, a 0 there, 3 is that one, minus 5, and a 1 for that alpha, beta, gamma term. So we could call these tripolynumbers. And if we're willing to sort of consider higher dimensional generalizations of this geometrical pattern, then we can extend this to sort of higher dimensional polynumbers. But actually, for us today, this three-dimensional one will suffice. Okay, so that's kind of along the lines that we've already been talking about in this series. And now we want to move in a slightly different direction by going to this bifield. That means we want to change our point of view so that we think of the coefficients now not as being integers, So that would be like polyint, coefficients from integers, and not polyrat, where the coefficients are considered to be rational numbers, but rather where the coefficients come from the bifield B2. That means they're all either 0 or 1. So in some sense, that's a much simpler situation. And we might call that poly B2, okay, to distinguish it from polyint, polyrat. Now we have poly B2. Okay, and it's really this framework here that now I want to say a little bit about. So it's at some level familiar, but it's also a little bit different. But the difference is a kind of a simplicity. It's a simpler kind of arithmetic because the arithmetic here is just so much simpler in some ways than the arithmetic in these two areas. Okay, so although this is quite elementary, there's a subtlety to it. So let's be careful about saying precisely what's happening here. I want to show you arithmetic with this framework of poly B2. And in B2, there are only two operations. There's addition and multiplication. Really, addition and multiplication mod 2 with zeros and ones. Okay, so we're going to extend that to an arithmetic with polynumbers. And for specificness, let's consider tri-polynumbers. So polynumbers in alpha, beta, and gamma. And let's just choose rather arbitrarily these three as an example. So P is 1 plus alpha plus gamma, Q is beta plus beta gamma, and R is 1 plus beta plus gamma squared. And you can see these really are in poly B2 because the coefficients here are all zeros or ones. All zeros or ones. Okay, so how do we do arithmetic with these things? Well, to add them, we add them, but we do so with the arithmetic mod 2. So P plus Q, we get a 1, we get alpha, we get beta, we get gamma, we get beta, gamma, we add them all up. What about P and R? Well, we get 1 plus 1. But what is 1 plus 1? It is 0. So there's no constant term. We have an alpha, we have a beta, we have a gamma squared. And what about Q plus R? Well, there'll be a 1, but there's a beta and a beta, and beta plus beta is 0. In the Boolean world, x plus x is always 0. Whenever we have 2 of anything, it disappears. So we have 1 plus 0 plus gamma squared, and there's the beta gamma there. What about the product? Let's look at just P times Q. So here's 1 plus alpha plus gamma. Here's beta plus beta gamma. How do we multiply them? Well, we just use the distributive law. So 1 times this is beta plus beta gamma. Alpha times this is alpha beta plus alpha beta gamma. Gamma times this is gamma beta plus gamma beta gamma. And there's a bit of simplification because there's a beta gamma here and there's another one right there. So those two will cancel. We'll just be left with beta plus alpha beta plus alpha beta gamma, and this one is beta gamma squared. So the arithmetic here is much like that in polyint. It's almost the same as doing integer arithmetic with polynumbers, except that the coefficients are always reduced mod 2. So even coefficients, even integers, become 0, and odd integers become 1. So this is a simpler arithmetic for sure because of this much simpler reduced aspect of the bifield, which only has 2 elements. Now, polynumbers are not functions. I know that in primary school you may have learned that a polynomial is a function of a certain kind, but that's not the way we're thinking about things. A polynumber is an expression of a certain kind. Nevertheless, a polynumber can act as a function. We can make it act as a function by evaluation. So let me illustrate. Let's say that R is 1 plus beta plus gamma squared. So that's a poly B2. We're working in poly B2, so everything has coefficients 0 and 1. So let's evaluate this thing now. So we can evaluate it, say, at 1, 0, 1. because it's actually a tri-polynumber. So we can substitute alpha equals 1, beta equals 0, and gamma equals 1. So we'll get 1 plus 0 plus 1 squared, which is 1 plus 1, which is 0. So when we substitute or evaluate it at these three numbers, we get 0. If we evaluate it at, say, 0, 1, 1, alpha is 0, there's no alpha, no problem. Beta is 1, gamma is 1, then we get 1 plus 1 squared, which turns out to be 1. If we evaluate it at 1, 1, 1, then we get 1 plus 1 squared, we get 1 again. And now consider this closely related but distinct polynumber. It's called t. It is 1 plus beta plus gamma. Almost the same, except that there's not a gamma squared, there's just a gamma. Okay, now it's immediate to see that this thing here will evaluate on these three things in exactly the same way. We're going to get 0, 1, and 1. In fact, we can see that it's going to be evaluating the same as r is on any input because of the fact that x squared is always x in B2. This is one of Boole's crucial observations about the arithmetic in his framework, that x squared always equals x. So that means that when you apply gamma squared to anything, it's the same as applying gamma to anything. So r and t are equal as functions, though they are distinct as polynumbers. They're distinct as polynumbers because they're just not the same lists. The one here is in a different spot to the one here. It's in a different place. So they're different polynumbers. But as functions, they are equal. Now, this is something that's a new phenomena that you see when you go to finite fields, that you don't see with the rational numbers or the integers. Okay, it takes some getting used to. The realization that you've got these two polynumbers which are distinct, but as functions they're completely identical. That doesn't happen over the rational numbers or over the integers. If two polynumbers are different, they are going to act differently as functions. Maybe not on everything, but you'll be able to find something that they act differently on. Not here. So this is a very good reason for us to separate in our minds very clearly the idea of a polynumber and the idea of a function. Okay, they are separate things, and this difference is especially noticeable here in this finite field or bifield situation. Same thing happens over other finite fields. Okay, so that's something we have to be very aware of. It has actually major ramifications, even for calculus, as I will eventually explain in my algebraic calculus course. Now, this distinction that we've just seen between polynumbers and their role as functions motivates us to introduce what we call Boole polynumbers, which is a subtle kind of distinction. They're almost like polynumbers, but not quite, and they're going to be the ones that play the important role for all this electrical engineering story. Okay, so a Boole polynumber, what is it? It's a polynumber expression in the B2 world, so everything is with coefficient 0, 1, and there's only plus signs and multiplications. But in A, B, C, capital A, capital B, capital C, instead of alpha, beta, gamma, and so on. With, and here's the crucial thing, no power greater than 1. No power greater than 1. So for example, have a look at this thing here. We've seen this before. 1 plus A plus B plus C plus AC plus ABC. This is a Boole polynumber because the power of any one of these variables that are appearing is at most 1. 1 is the maximum exponent that you see. In fact, so you don't see any squareds, you don't see any cubes or higher powers. On the other hand, this thing here, C, which is A plus B plus A squared, it's not a Boole polynumber because that A there has an exponent of 2. Okay, so Boole polynumbers are especially simple kinds of polynumbers, but to make it clear that we're talking about Boole polynumbers and not regular ones, we're going to switch from alpha, betas, and gammas to capital A's, capital B's, and capital C's, and so on. And let's introduce this type. So poly-Boole will denote the type of Boole polynumbers, as opposed to poly-B2. Okay, so now a theorem. That if P is a B2 polynumber, then there's a unique Boole polynumber, P tilde, such that P and P tilde agree as functions. In other words, P of x equals P tilde of x for any x in B2 to the n, any suitable inputs that we're allowed to put in here. So in other words, given any poly number, there is a sort of a simplified version of it where all the powers are at most 1, which acts just the same way as the original one does when it comes to the idea of having a function. As functions, these two are not distinguishable. So let me illustrate the theorem with an example, which will also show why it's true, or how to obtain the tilde from the original. So let's suppose that we're in dimension 3. So we're talking about tri-poly numbers. So here is a tri-poly number P, which is 1 plus beta plus alpha beta plus beta squared plus beta gamma cubed plus alpha squared gamma to the 5th. Okay, now suppose we evaluate this polynumber on 3 Boolean numbers A, B, and C. So each of these is 0 or 1, and we're evaluating it. So that means we have to replace the alphas with A's, the betas with B's, and the gammas with C's. So we get 1 plus B plus AB plus B squared plus BC cubed plus B squared C to the 5th. Now, these are all numbers from our bifield. And so the crucial property of Boole, that x squared equals x, means that we can replace this b squared with a b. We can replace this c cubed with c. Because if c squared is equal to c, then c cubed will also be equal to c. Because c cubed is c squared times c, which is c times c, which is c. And any power of one of these numbers is going to be equal to the original number. So this thing becomes BC, and this one becomes BC as well. So sort of like rubbing off the exponents. We get to rub off all the exponents. And now there are no exponents bigger than 1. But now there's a further reduction that can happen, because we can see there's 2 B's here. And there's also 2 BC's. So they disappear and they disappear. We're just left with 1 plus AB. So in other words, this P tilde and this P act exactly the same way on any inputs that we're talking about, like 3 inputs. Even though the actual objects, the polynumbers, are quite different. It's a polynumber. This one has all kinds of higher power terms. This one doesn't. So this is a phenomenon, let me repeat, that does not happen with rational or integer arithmetic. So it's a new phenomena for you. Okay? So it doesn't make sense to define this over the rationals or over the integers. But over a finite field or over a bifield, it does make sense. Okay, so what we are saying, this theorem tells us that if we're interested in functions, we can restrict ourselves just to Boole polynumbers, because every polynumber as a function is effectively the same as a Boole polynumber as a function. Okay. Now, the Boole polynumbers are a manageable cohort because the sizes are constrained. So for example, here's the theorem that there are exactly 2 to the 2 to the 3, in other words 2 to the 8, Boole tri-polynumbers. Exactly 2 to the 8, that's 256. And why is that? Well, because any such Boole tri-polynumber will be of this form. It'll be some coefficient times 1 plus some coefficient times a plus something times b plus something times c plus something times ab plus something times ac plus something times BC plus something times ABC. The possible terms that you can write down that involve each variable at most to the first power is really exactly the same as the set of subsets of three things. Right? These are basically kind of listing all the subsets of A, B, C. And there's 8 of them. And since there are 8 possible blanks to be filled in with each coefficient being either 0 or 1, there's 2 times 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 2, or 2 to the 8 possible different Boole polynumbers when we have 3 inputs, or dimension 3. Okay, so if we wanted to go to n dimensions, then a Boole polynumber, probably better to be an expression in, say, a1, a2 up to an. Instead of a, b, c, we'll use this. And then it's made of b2 linear combinations of, well, terms corresponding to sort of choosing subsets of 1 through n. So if we choose a subset, I1, I2 up to ik, of the set 1, 2 up to n, then from that subset we can create a term, the product of a sub I1, a sub I2 up to a sub ik. And that will then be a constituent, one of 2 to the n such constituents that we can add together to create a general Boole polynumber in this dimension. And so since there are 2 to the n such subsets, there are going to be exactly then 2 to the 2 to the n Boole polynumbers of dimension n. There will be 2 to the 2 to the n Boole polynumbers of dimension n. This number happens to be exactly the same as the number of Boolean functions of dimension n. If we want to talk about the things of dimension n, we might say polybool n. Okay, that represents things of dimension n. So when there's n is 3, those are the ones we were talking about already. And now we come to a happy result that brings together these 2 central objects in our analysis. The objects are the Boolean functions of dimension n and the Boole polynumbers of dimension n. And we might call this the Boole polynumber evaluation theorem. It asserts that these 2 objects are isomorphic, that the Boole polynumbers of dimension n are isomorphic to the Boolean functions dimension n. And they're isomorphic in what sense? Well, actually it's quite a strong isomorphism. They're isomorphic as algebras of Boole. So what does this mean? So it means, at least at first this here, that if we're given a Boolean function f, so I remind you what a Boolean function is. It's a function that takes b2 to the n to b2. Okay, so it's a function on n tuples of zeros and ones. This is the Boole algebra. It's a function from the Boole algebra, assigning each element of the Boole algebra to either a 0 or 1. Okay, such a function f, we then get a unique Boole polynumber, let's say b sub f, in Boole poly n, which has the property that if we evaluate f on an n tuple, a1, a2 up to an, that's the same as evaluating this polynumber b sub f at a1, a2 up to an. Where the ai's, maybe I should say, the ai's all belong here to our bifield. So this is great. So for every Boolean function, there is a unique Boole polynumber. Okay, and this matching is a complete matching. It's a beautiful matching that respects the linear structure and respects actually the multiplicative structure as well. And so it tells us that this b sub f, this polynumber, is then an algebraic invariant for any circuit which has output f. Because these Boolean functions arise as outputs of circuits. So we have some complicated circuit. We make a truth table for it. We look down the column of that truth table that we've made. That's a Boolean function. And this theorem is now telling us that we can represent that Boolean function by a Boole polynumber. There's a unique Boole polynumber that will represent that particular function. And so any circuit that creates that particular Boolean function will be associated to the same Boole polynumber. And this is really the heart of the power of Boole's algebra, of the algebra of Boole, to deal with circuit analysis, because we have this lovely correspondence between circuits, truth tables, and Boole polynumbers. So let me illustrate this with a nice little example. And I chose an example that's actually treated in a nice video by Mandy Orzechowski, and I'll put a link to it in the description. So this is the logic gate that she considers. And we have inputs A, B, and C. And here's a truth table, or evaluation of this output F in terms of A, B, and C. So let's analyze it. So here we have a not and a not. These are inverters here. We have a couple of ands, and we have an or. So what's happening here? So if A is coming in here, then we have A bar here. She works in the Boolean framework. We're going to be working in the algebra of Boole. So the inverter is 1 plus A. So we have 1 plus A out here. And here we have B. So this is 1 plus A and B. That's a product. And then that's ANDed with C. So it's really just multiplied by C. So the output here is this first term here. And then we have an OR gate. So our OR is represented by the circle sum. And what's happening here is we're having B inverted. So there's 1 plus B coming in there. And this is also A here. So 1 plus B times A. Now, to analyze this, we want to shift to the algebra of Boole. So we have to convert the inclusive OR to our operation of exclusive OR, the addition sign of the algebra of Boole. So how do we do that? Well, we know that x circle sum y is x plus y plus the product xy. Okay? X plus y plus xy. So we have to take this, 1 plus a times b times c. We have to add 1 plus b times a. And we also have to add the product of these, which is 1 plus a b c there and 1 plus b a there. Okay, we expand. We get bc plus abc plus ab. And then there's a common factor of abc multiplied by 1 plus a, 1 plus b. We're really only doing polynomial algebra here, right? This is not Boolean algebra. We're just using high school manipulations with polynomials or polynumbers. Okay, but now this simplifies a little bit because, well, there's an A here, there's an AB, there's a BC, there's an ABC there, fine. And what about all of this? Well, ABC, when we multiply that by anything, the only effect will be to jack up the powers, okay? But if we're working in the algebra of Boole, a squared is the same as a, b cubed is the same as b. So each one of these four things that we're multiplying by will have the effect of giving us another ABC. So the result of this will be 4 copies of ABC. And since 4 is the same as 0, they all disappear, and we just get a plus ab plus bc plus abc. And this is a Boole polynumber. This is not, but this is. And this thing is now unique. It's unique. There's only one of it. And that's the b sub f. That's the b, the Boole polynumber that the theorem guarantees will always be available for any function f. In fact, we know how to create this thing, right? I mean, we don't have to use the Boolean expression. We know how, I told you this before, we can look at the places where this thing is 1, and then we create a corresponding sum of products for that. Okay, if we want to evaluate this thing to get the actual truth table, how do we do that? Well, this is just a function. This is a function of a, b, c. We just input different values of a, b, and c. If they're all 0, then we get 0. If two of them are 0 and C is 1, so C is 1 but the others are 0, we're going to get 0. If only B is 1, that's 0, that's 0, that's 0, that'll still be 0. If B and C are 1, that's 0, that'll be a 1, that'll be 0, that'll be 0, so we get a 1. If A is 1 and the others are 0, that'll be 0, 0, 0, so we'll get 1. If A and C are 1, then that's going to give us a 1. That's 0, that's 0, that's 0, we're still going to get 1. And when A and B are 1, that'll be a 1, that'll be a 1. So we'll get 0. And when all three of them are 1, we get 1, 1, 1, 1, that's still 0. So that's what we pick up, which is the same thing that Mandy got for her Boolean algebra analysis. So we're starting to see here the reason why the algebra of Boole is so powerful, because first of all there's a unique Boole polynomial or Boole polynumber for a given circuit or a given truth table, and this is an invariant. So we can tell when two circuits are equivalent just by computing the corresponding Boole polynumbers. And there's no question at all about telling whether two of those things are equal, because you just look at them as polynumbers and they're equal, or if they have exactly the same coefficients, and otherwise they're not. In the Boolean algebra, that is a major headache, trying to decide whether this Boolean expression is equal to this Boolean expression. This is a very, very hard problem. Okay, it's like requires rocket science technology. Okay, here we do not need that. We're just evaluating, we get polynomials essentially, if you like, and it's just whether this polynomial is the same as this polynomial. That's all there is to it. And in terms of creating a truth table as a result, that's just evaluation. So your computer evaluates polynomials, in this case just reduce it mod 2 at the end. So creating a list like this is a piece of cake with the algebra of Boole point of view. So next time we want to put all of this to work to solve kinds of problems that electrical engineers want to do, and we're going to use the algebra of Boole to do it. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.